All right, let's get right into it. In the world of machine learning, there's this idea that more data is always better. But what happens when you have too much data? So many different features that you can't see the forest for the trees. Well, today, we're going to demystify a really powerful technique called Principal Component Analysis, or PCA, that helps us find that all-important signal inside all that noise. So here's our game plan. We'll kick things off by talking about the too much data problem. Then we'll unpack the big idea behind PCA and see it work its magic on the classic Iris Dataset. After that, we'll hit a common snag involving something called sparse data. And finally, we'll meet the tool that's built to solve it, TruncatedSVD. First up, let's really dig into the core challenge here. Why do we even need a tool like PCA in the first place? I mean, this is the question, isn't it? It's at the heart of so many data science projects. We spend all this time and energy collecting information, right? Adding more and more columns, more and more features to our datasets. But does that automatically lead to better answers? And the answer, maybe surprisingly, is a big no. In machine learning, just dumping every piece of data you have into a model isn't always the best move. A lot of those features might be redundant or totally irrelevant, and they just create a kind of statistical noise that can actually confuse your algorithm. It makes it way harder to spot the patterns that really matter. We need a way to filter all that junk out. And that brings us to the really elegant solution. So let's pull back the curtain on the core concept that makes PCA tick. The whole strategy is called dimension reduction. And honestly, the name says it all, right? It's all about taking our original high-dimension dataset and creating a new, lower-dimension version of it that still holds on to the most important information. Okay, so how does PCA decide what's important and what isn't? This is the cool part. PCA works on one big assumption. The most important features are the ones that have the most variance, the ones that change the most. It takes our data, rebuilds it into a new set of features called principal components, and then it ranks them. The components with high variance, that's your signal. The ones with low variance, PCA treats that as noise and gets rid of it. This is a perfect way to picture it. You can see the variance of each new feature plotted right here. PCA basically draws a line in the sand. It keeps the components over on the left, the ones that capture a ton of the data spread, and it just tosses out the ones on the right. It's a really simple but often super effective way to clean house. So that's the theory, but talk is cheap, right? Let's see how this actually works in the real world. We're going to put PCA to the test with a very famous dataset. We're talking about the Iris Dataset. It's a classic in data science for a reason. It's got measurements for 3 different species of iris flowers, and each flower is described by 4 features, things like petal length, petal width, and so on. Our goal is to see if we can simplify this data down without losing the ability to tell these 3 flower species apart. And here's the code using Scikit-Learn. It's incredibly simple. You import PCA, you create the model, and you just tell it how many components you want to keep. In this case, we're asking it to boil everything down from 4 features to just the 2 most important ones by setting n components equals 2. And boom, just like that, the job is done. We've taken our data from 4 dimensions down to just 2. We've literally cut the complexity in half. But the real question is, did it work? Just look at this scatter plot. It's amazing. The 3 different species form 3 totally distinct clusters. Even though we threw out half of our data, the essential structure that separates them is still perfectly clear. And here's the really crucial part. PCA didn't know anything about the species labels. It just found the 2 directions with the most variance, and it turns out those were exactly the directions we needed. So PCA seems like a magic bullet, doesn't it? But like any tool, it has its limits. And that brings us to a really common situation in data science, the challenge of dealing with sparse data. Think about data you get from analyzing text. You might have a huge grid where every row is a document and every column is a word from, say, the entire English dictionary. The numbers in the grid tell you how many times each word appears in each document. Well, guess what? Since most documents only use a tiny fraction of all possible words, that grid is going to be overwhelmingly full of zeros. We call data like this sparse. And to handle it without using up a ridiculous amount of computer memory, we use a special format. It's called a compressed sparse row matrix, or CSR matrix. And it cleverly only keeps track of the non-zero numbers and where they are. And here's the catch. Here's where we hit a war. If you try to feed one of these super efficient CSR matrices into the standard PCA tool we just used, it's going to give you an error. It just wasn't built to handle that sparse data format. So what do you do when your favorite tool can't handle the job? Well, you call in a specialist, and in this case, it's time to meet TruncatedSVD. The best way to think about TruncatedSVD is as PCA's cousin, one that's specifically built for sparse data. So while PCA wants those normal, dense arrays, TruncatedSVD is designed to work directly with our CSR matrices. But here's the really fantastic part. They have the exact same goal, dimension reduction, and the way you use them is almost identical. And this slide just makes it crystal clear. The code for TruncatedSVD is basically a mirror image of the PCA code. You import it, you tell it how many components you want, you fit and transform your data. The only difference is that this time, it happily accepts that sparse CSR matrix as import. No errors, no problem. It just works. All right, let's bring it all home. What's the bottom line here? First, dimension reduction is a vital tool for simplifying complex data. Second, PCA is your star player for the job. It works on that key assumption that high variance means high importance, and it's fantastic for dense data. But, and this is a big but, when you run into sparse data, those CSR matrices, you just need to swap in its sibling, TruncatedSVD. And that kind of leaves us with one last big thought. You know, tools like PCA and TruncatedSVD are more than just lines of code. They get at a fundamental challenge of our information age. As we keep collecting these oceans of data, the most valuable skill isn't just gathering it, it's learning how to distill it. It really makes you wonder, in a world of big data, what information is actually essential and what is just noise?